The last video showed us what a critical number was. Remember that a critical number is a value that when you plug it into the derivative, you get either 0 or undefined. And the reason we call these values critical numbers is because if a continuous function has a relative extremum at a particular value, then that particular value is a critical number. So extrema are considered to be important points. In fact, some may say critical points. So critical numbers are important in finding critical values, namely the extrema of the function. So let's take a look at this if-then statement. If a continuous function has a relative minimum at x equals c, then c is a critical number of f. Well, let's see if we can flip that around. Is the converse true? Namely, if c is a critical number of f, then is there a relative extremum at that critical number? In other words, finding critical numbers, does that guarantee a maximum or minimum? Okay? Just because the derivative equals 0, or just because the derivative is undefined, does that guarantee that there is a maximum or minimum there? So pause the video and think about it. See if you can come up with an example that may disprove the converse of that statement. Perhaps you came up with h of x equals x cubed. Let's see if we can figure out what the critical number of this graph is. Well, to find the critical number, we take the derivative of the function, and we find the derivative is 3x squared. That's a fairly trivial derivative. And we can either set this equal to 0 or ask what values of x cause 3x squared to be undefined. Of course, 3x squared is never undefined, so let's just set this equal to 0. And when 3x squared equals 0, that's only going to happen when x equals 0. So the question now is there an extremum on x cubed when x equals 0? And the answer to that should be a fairly obvious no if we remember what the graph looks like. If we look at this graph, we have, it's kind of like a parabola on the right side, but it's an upside down parabola on the left side. And we've got this point right here, x equals 0, where we've got a horizontal tangent line. Is it a maximum? No. Is it a minimum? No. But it does have a horizontal tangent line. What doesn't happen is a turning around point. Okay, so that's going to come up a little bit later. But for now, let's just focus on the fact that the converse of that statement is not true. Although it is true that if we have an extremum, then it happens at a critical number. We cannot say that if we have a critical number, we have found an extremum. And here's a good counterexample with this x cubed. So the extreme value theorem is the theorem that we're talking about now. That's the one that that guarantees that we have a maximum or a minimum. And what the extreme value theorem basically says is that when we have a continuous function on a closed interval, then we guaranteed we'll have some sort of value, some sort of point on this closed interval that is an absolute maximum, and some sort of point on this closed interval that is an absolute minimum. And furthermore, those absolute maximum, that absolute maximum and that absolute minimum must occur at one of two places. Either those maxes and mins will occur at a critical number, i.e. where the derivative equals 0 or is undefined, or those absolute maxes and mins will happen at the endpoint. Okay, so this is one of the three value theorems. We've already done the intermediate value theorem, so this is the second of them. This is the extreme value theorem. Pay close attention to the next section because that will be the third and final value theorem. All right, so let's see if we can figure out how this works with this particular function. We are going to try to find the extrema on the function of the function f of x on the interval 0 to 3. We know that there will be an absolute maximum. We know there will be an absolute minimum because we know that this function is continuous. This function is continuous because all polynomial functions are continuous. So the first step is find the critical numbers. And remember that the critical numbers are places where the derivative is either equal to 0 or undefined. So the derivative is easy to find. 3 times 2 is 6. 6, and then we drop the 3 down to a 2. The derivative of negative 6x is negative 6. This is another polynomial. It's always defined, so it's never going to be undefined, but it does sometimes equal 0. In fact, it equals 0 at x equals plus or minus 1. All right, negative 1 is not in this interval, so the only critical number we care about is x equals 1. All right, so the extreme value theorem says that our absolute maximum is either going to happen at 0, 1, or 3. Our absolute minimum is going to either happen at 0, 1, or 3. Those are our only possible scenarios, okay? So what we're going to do is we're going to evaluate our given function at the endpoints of 0 and 3, and also at our critical number of 1. F of 0 is 2 times 0 cubed minus 6 times 0, which is 0. F of 1 is 2 times 1 cubed minus 6 times 1, which is negative 4. And F of 3 is 2 times 3 cubed minus 6 times 3. That one's a little harder, so let me think about that a bit. 27 times 2 is 54, and 6 times 3 is 18. 54 minus 18, I think that is 20, no, let me think about that. It's 36, yeah, 36, okay, good. So these are the potential extrema. So we ask the question, which one is the biggest number? Which one is the smallest number? That's pretty easy. I could ask any second grader to find the, well, maybe not negative numbers, I take it back, but we can ask any, let's say, fifth grader, which one of these three numbers is the smallest, which one of these three numbers is the largest. The smallest one is the absolute minimum on this interval. The largest one is the absolute maximum on this interval, and we're done. So we look at the smallest value is negative 4, so f of x reaches an absolute minimum of negative 4 at x equals 1. Furthermore, f of x reaches an absolute maximum of 36 at x equals 3. We know that there's going to be an absolute minimum somewhere on this closed interval, and we know that there's going to be an absolute maximum somewhere on this interval. And when we test our endpoints and our critical numbers, we determine what those maxes and mins are. Okay, so pay attention to the terminology here. When we're talking about the extrema, we're talking about the y values. We're comparing 0 and negative 4 and 36. Okay, so the largest one is the maximum, the smallest one is the minimum. Sometimes they'll ask where these values occur, and those locations are going to be determined by the input, the independent variable, in this case the x value.